Okay, so this is Year 9 Part 3. In the last part, we were talking about constructive, destructive and conservative plate boundaries, and we're going to come on to that in a bit more detail. So, quick little recap. You've got the inner core, outer core, mantle and crust. So let's have a look at the crust in a bit more detail, because that's the one we haven't looked at much yet. So if you've got the crust of the Earth, it's a bit like an egg that's been tapped. So a hard-boiled egg, it's been tapped. What you've got is, you've got a shell. We call that eggshell the crust. And that's the whole eggshell. And then each bit of eggshell is called a plate. And where two plates meet, that is known as a plate boundary. And then depending on what those plates are doing will determine what kind of boundary it is. So if you've got two that are going into each other like that, we call that one a destructive boundary, because land will be destroyed when they collide into each other. Either it's a destructive boundary, you can have a few things happen. So if they go into each other, either you'll get a mountain being formed like the Himalayas, where they're both being pushed into each other and going upwards, or you'll have one going underneath the other, and you have a subduction zone, and then when this one goes underneath it, this will melt up because it'll get hot and it'll come back up as a volcano. Okay, or you could have one where you might have one where they're both moving away from each other, and that's a constructive plate boundary. And here you'll have new magma come into the surface and it'll make a ridge. Okay, and so things like the Mid-Atlantic Ridge in Iceland, again lots of new land being formed, and you see magma come into the surface because the crust is quite thin, and you get some earthquakes, not so many volcanoes. Okay, or you might have a bit of the world where you've got two plates that are just going side by side, and that is known as a conservative plate boundary. Okay, because no land is lost or gained, they're just moving past each other, and there you get a lot of earthquakes, places like the San Andreas Fault. Okay, so next up, what we've got is, okay, what effect does those plate boundaries have on the Earth? Well, millions of years ago, what scientists think is they think that the Earth, the continent of the Earth, so if that was all of the land on Earth, was all in one place called Pangaea, and the rest of it was sea. And the reason why they think this is because if you look at the Earth today, that was South America, that's Africa, for example. What you notice is, you'll notice that there'll be a band that runs through it like this, and in that band they will have the same fossil record, which tells you that at one point these two places were probably touching and animals could walk between them. Okay, so it was probably somewhere like here on Pangaea, okay, where they could walk, so the animals just walk from one place to another. Okay, and where these type of animals live, that might have been like that. Okay, so that's why those fossils there and there are the same. So we've got the fossil record across the oceans, it's the same in strange bands like that. The other thing that you'll notice is if you look at the rocks, the sedimentary rocks, so the layers of rocks, they'll be the same as well. On both sides, and that would only happen if they were laid down on top of each other, say here, all together, and then slowly spread apart over time. Okay, and the last one is one called jigsaw fit basically, if you look at a map of the world today, it looks like some of the bits used to fit together, so we call that jigsaw fit. So they're the three pieces of evidence: fossil record, rock record, and the fact that it looks like it used to fit together, and we call that jigsaw fit. And nowadays we can actually track how fast they're moving. So the evidence that we've got nowadays is from satellite technology. We can track exactly how fast these are moving, but when this theory first came about, we couldn't do that. We had to rely on the fossils and the rocks, and the fact that it looked like it used to live together. But now it's been absolutely definitely proven that the continents are moving, and we know exactly how fast they're moving because we can take images over a course of a year, and satellites can pinpoint exactly how far they've moved. Even if it's like centimetres over a couple of kilometres, they can tell that.